So good morning students, today we are going to discuss about the velocity analysis of a slider crank mechanism. So over here you can see there is a classic diagram of a slider crank mechanism. There is a crank, as you can see, the crank from here to here, this is AB. So the crank can rotate in a circular path as shown in the dotted line. That means point B of this crank can rotate in a circular path, whether it is in clockwise type or anti-clockwise type of motion, doesn't matter, but it can rotate. Complete rotation can occur in 360 degree. And this is called the connecting rod, that is BC. If you consider that this is point C, so BC is the connecting rod. So when the crank rotates, then obviously the connecting rod, it will definitely reciprocate. Now which part will reciprocate? Point C will reciprocate. And what will happen to point B? Point B will rotate. So point B will be under rotation and point C will be under reciprocation. Okay, so now we are going to draw the velocity diagram of this particular space diagram. Okay, so for that, what we need to draw first, that is reference x and y axis, which is actually two mutually perpendicular axes. These are the two mutually perpendicular axes. I am doing by my common sense, but better you should not draw it like that. Use your instrument protectors and compass for drawing the x and y axis accordingly. So from this particular space diagram, we can find out that there are two different points, point A and point D. Point A and point D, which are actually motionless, which doesn't have any motion. So obviously from the logic or from the law of the velocity diagram, we must put them in the origin. So point A and point D, they are kept at the origin. Now, as you know that for each and every velocity analysis type of problem, whether it is for four-bar mechanism, whether it is for slider crank mechanism, or whether it is combination of four-bar and slider crank mechanism, at least one of the complete set of data will be provided. That means not only the length of the crank and connecting rod, and as well as the distance between this crank and connecting rod and the angle theta, etc. It should be provided with real data, but also the value of omega in RPM, it will be given, or we know that omega equal to 2 pi n by 60. So maybe in some particular numerical problem, the RPM of the crank, that is capital A, that will be given. So from here itself we can find out what is the value of omega. Now for the crank we know the omega value equal to omega of B with reference to A. So we will call it omega BA. Now when the connecting rod is having a rotational type of movement, so definitely one more omega will be generated at that particular link BC, which is the connecting rod. So over there the omega will be omega CB. Okay. So in the velocity diagram, what they might ask? First of all, they will ask you that find out the velocity VBA, find out the velocity VC with reference to D, and find out the velocity VCB. So these are the three velocity that we have to find out. So this is our question. And after that, they might ask you that find out the omega CB also along with that. Okay. So this is the basic mode of a question. So the questions may come in that way. So how to solve this? As you have done previously in the four-bar mechanism, so over there we know that the method to solve this type of problem, that first of all at VBA we have to find the local coordinate, or we have to draw a local coordinate over here. Something like that, okay, and we have to find out that what is the positive angle VBA with the positive x-axis. We have to find out that particular angle value. So what is the method? The method is very simple. So what we are going to do, that using a compass, we are going to measure a line, something like that. Okay, and we have to find out what is the distance from here to the intersection point. Okay, so we got the intersection point. So if this is the intersection point over here, so we can connect these two in this way. Got it? So this is the line of VBA, but what exactly the magnitude of VBA, that still we don't know. But in the numerical problem, they definitely are going to provide us this information, that is the length AB will be provided to you, as well as this omega BA will be provided to you. Now we know that VBA, that is equal to length AB multiplied by omega BA. Got it? So you are having these two real data. Okay. So if you know these two real data information, then you can find out the value of VBA. So suppose you are getting the VBA value equal to 500 millimeter per second. Suppose you are having a value something like that, 500 millimeter per second. This is the velocity value you got, putting these two values. So which length of VBA you are going to take in the velocity diagram? That is the main question. So what you have to do, you have to take suitable scaling factor. Okay? You have to take suitable scaling factor. Now suitable scaling factor means what? Suitable scaling factor means it entirely depends on you people, that what are the scaling factor you are going to take. You may consider that each 10 millimeter per second velocity is represented by 1 millimeter length in the velocity diagram. Or if you wish that each 20 millimeter per second velocity is represented by 1 millimeter length in the velocity diagram, that's up to you. No problem. You can take that. What does that mean? That under this situation, 500 millimeter per second length is represented by only 50 millimeter in the velocity diagram. Now you can draw this 50 millimeter length in your copy in the velocity diagram easily. Got it? So when you are going to do this, suppose this length, now I am going to remove this line. Actually this line can create some confusion, so I am going to remove this construction line. Suppose this 50 millimeter length is somewhat like that, from here to here. Got it? So this 50 millimeter length, the limit is over here, and we call it point B. We call it point B over here. Okay. So this is the length, point B. So AB. Now the direction is very important. So this is the direction. So we got the real direction, real dimension of the velocity V, B, A, something like this. Simple, isn't it? Next, this particular vector, velocity C with reference to D, is acting in a straight line along the x-axis in the left-hand direction. So simply, we are going to draw a straight line in the left-hand direction, just like this. Okay? No need to mention that this left-hand side straight line is actually the line of VCD. It is the line of VCD. Now next, that is velocity VCD. Velocity of C with reference to B. So where is B in the velocity diagram? The point B is over here. Okay. So from point B, there must be one vector which will be acting in this particular direction. Downward left side, slightly downward, slightly left hand side, something like that. But there is a method, as I told, that what we have to do, we are going to draw again a local coordinate, something like this, and then we are using the compass and just draw an arc. Similarly, from this particular point B, we are going to draw the same arc over here, and in the same way, we are going to draw a vertical line over here. Okay. So from that vertical line, we have to find out the intersection point. So where is the intersection point? Over here. Where is the intersection point? So this is the length of the intersection from here to here, a very small length. So from here to here there is a very small length, that is called the intersection point, which we are going to find over here. Okay. So like that, we have identified the point of intersection over here, which is represented over here also. So if you are going to join them together from point B, then we will find out that this new line, which is a line of velocity C with reference to B and velocity C with reference to D, they are having a common point of intersection, and that is over here, this particular point, and this particular point on the horizontal axis, So this particular point is named as point C, and from B to C, the direction of arrow will be like that. From B to C, the direction is something like that, and from A to B, the direction is like that. Okay. Now what you have to do? Now measure this length using scale. That is, what is the length in the velocity diagram? What is the length? Length you have to find out. Get the actual length of VCD and multiply it with the scaling factor. Length of VCD and multiply it with the scaling factor. So what you are going to get? You are going to get the real velocity value or actual velocity value. Okay. Same process can be applied for VCD. done. This is how, I guess all of you can see this right now. So this is how it can be done, that is VCD into scaling factor, the length VCD into scaling factor, that is the real velocity value of VCD, like that. So once you get the velocity of C with reference to D and velocity of C with reference to D, then the rest of the part is very simple, because we know that VCD, that is equal to omega CD multiplied by the length C. Now from this calculation and from this diagram, we know what is this value. It is known. In the problem, it will already be given as a given data. It is known. So only unknown is omega CD. So omega CD, that should be VCD divided by CD length, and similarly omega CD, that should be equal to VCD divided by this particular length. Sorry, omega CD is not coming. Omega CD cannot come because it is in a reciprocating motion. So there is no question of omega value in a reciprocating type of motion. Only it can having a linear value. It is having a linear value of motion, because the slider block, it is in a linear path, so there is no chance of generating the omega value or angular velocity value. So that is how the velocity diagram can be constructed, and it is the explanation. Clear?